So now, armed with the binomial probabilities, we can do the harder problems. So let's take the same experiment again. We flip a coin independently 10 times. So these 10 tosses are independent. We flip it 10 times. We don't see the result, but somebody comes and tells us, you know, there were exactly 3 heads in the 10 tosses that you had. Okay? So a certain event happened. And now you're asked to find the probability of another event, which is that the first 2 tosses were heads. Let's call that event A. Okay. So are we in the setting of discrete uniform probability laws? When we toss a coin multiple times, is it the case that all outcomes are equally likely? All sequences are equally likely? That's the case if you have a fair coin, that all sequences are equally likely. But if your coin is not fair, of course, heads is going to have a different probability than tails. If your coin is biased towards heads, then heads is going to be more likely. So we're not quite in the uniform setting. Our overall sample space, omega, does not have equally likely elements. Do we care about that? Not necessarily. All the action now happens inside the event B that we're told has occurred. So we have our big sample space, omega. Elements of that sample space are not equally likely. We are told that a certain event B occurred, and inside that event B, we're asked to find the conditional probability that A has also occurred. Now, here's the lucky thing. Inside the event B, all outcomes are equally likely. The outcomes inside B are the sequences of 10 tosses that have exactly 3 heads. Every 3-head sequence has this probability. So the elements of B are equally likely with each other. Once we condition on the event B having occurred, what happens to the probabilities of the different outcomes inside here? Well, conditional probability laws keep the same proportions as the unconditional ones. The elements of B were equally likely when we started, so they're equally likely once we are told that B has occurred. So to deal with this problem, we need to just transport us to this smaller universe and think about what's happening in that little universe. In that little universe, all elements of B are equally likely, so to find the number, to find the probability of some subset of that set, we only need to count the cardinality of B and count the cardinality of A. So let's do that. Number of outcomes in B. In how many ways can we get 3 heads out of 10 tosses? That's the number we considered before, and it's 10 choose 3. This is the number of 3-head sequences when you have 10 tosses. Now let's look at the event A. The event A is that the first 2 tosses were heads, but we're living now inside this universe B. Given that B occurred, how many elements does A have in there? In how many ways can A happen inside the B universe? If you're told that the first 2 were heads, So out of the outcomes in B that have 3 heads, how many start with heads? Well, if it starts with heads, then the only uncertainty is the location of the 3rd head. So we started with heads. We're going to have 3 heads. The question is, where is that 3rd head going to be? It has 8 possibilities. So slot 1 is heads, slot 2 is heads. The third head can be anywhere else. So there's 8 possibilities for where the third head is going to be. Okay. So what we have counted here is really the cardinality of A intersection B, which is out of the elements in B, how many of them make A happen, divided by the cardinality of B. And that gives us the answer, which is going to be 10 choose 3 divided by 8. So this is 8 over 10 choose 3. Okay, so we're going to close with a more difficult problem now.